We have all been fooled by black holes. Because if you look at it from pure physics, a black hole is not the ultimate destroyer of everything, but a power generator. In fact, any truly long-lived advanced civilization will sooner or later have to use black holes to obtain energy. Hearing this, you probably want to argue back. Don't we already have the sun's energy to use? But the truly deadly point lies in that very phrase, we have the sun. So next, let's not look at black holes just yet. Let's first make it clear where the upper limit of the stellar energy path really is. And then talk about how advanced civilizations would use black holes. First, we have to admit one thing, relying on starlight will eventually not be enough. Because stars may look bright, but as engines they are terribly inefficient. Take the sun as an example. The fraction of its mass that actually gets converted into energy is only about 0.7%. The rest is basically lost as waste heat, light, and various inefficiencies. For a young civilization, that is of course sufficient. But once you stretch the time scale to billions of years, the problem suddenly becomes brutal. Because stars live off nuclear fusion, and hydrogen is finite. The result is simple, stars will run out, grow old, and go dark. You can rely on them to live a bit longer, no problem. But if you want to rely on them for a very, very long time, you will eventually hit a hard wall called fuel. So is there a more ruthless path? There really is. Gravity is different. Gravity does not burn out and does not stall, it only keeps pulling. And precisely because it keeps pulling, as long as there is a downward tendency, there is usable gravitational potential energy. So when we look for an ultimate power source, our target should not be a quietly shining star, but something that can lock energy into gravitational structures, such as a black hole. But there is a filter here. Not just any black hole will do. Because a non-rotating black hole is more like a simple drain. It is very hard to extract stable, sustainable output from it. What we are really looking for is a rotating black hole, also known as a Kerr black hole, because rotation means that part of its energy is stored in the form of spin, and in theory, that energy can be extracted. Why does it rotate? Because in the explosive birth of a singularity, a collapsing star rarely falls straight down. It usually twists and spirals as it collapses. Conservation of angular momentum compresses this rotation faster and faster, to a mind-numbing degree. And more importantly, this is no longer just a ball spinning. It is more like space-time itself being twisted into a vortex. You can think of it as a gigantic flywheel. The faster the flywheel spins, the more kinetic energy it stores. A rotating black hole is the ultimate flywheel. It locks the rotational energy of a dead star inside a gravitational cage. And now comes the real shock. If you break down the energy budget of a rotating black hole, you find something deeply counterintuitive. Not all of its total mass energy is locked forever behind the event horizon, unreachable. A significant portion of the energy is actually tied up in rotation and can, in principle, be accessed and extracted. The upper limit can reach as high as 29%. That is to say, in the total mass energy of a rotating black hole, up to about 29% is purely rotational energy. Even if you extract only a small fraction of that, the scale could still surpass the total lifetime output of the sun. So in the end, what we want is not an ordinary power plant, but a power station built around a black hole. Future engineers, looking up at the night sky, will no longer see darkness as emptiness, but as an unmined energy field. Black holes will no longer be predators to avoid, but resources, harvestable energy sources. But recognizing a black hole as a battery is one thing, actually wiring it up is another. Stars send energy outward. You just put up a solar panel and collect it. Black holes are the opposite. They drag energy inward and grip it tightly. If you want to take it, you have to step in and make an exchange. But you cannot touch the event horizon itself, because that is forbidden territory. Cross it, and you never come back. So the only workable region is just outside the event horizon, hugging it closely. For a rotating black hole, there is an additional boundary outside this region, forming a special shell known as the ergosphere. The name is not metaphorical, it is literal. This is where work can be done. The reason lies in frame dragging. The black hole drags nearby spacetime along with its rotation. As a result, inside the ergosphere, it is almost impossible to remain stationary. This does not mean you can outrun light. It means that remaining at rest relative to the distant universe is impossible here. You are forced to rotate along with the black hole, and it is precisely in this violent work zone that the Penrose process can occur. The idea is elegant, but the execution is deeply counterintuitive. You send a container of matter into the ergosphere, moving along the direction of the spin. Then, at an extremely precise moment, you split it into two parts. The first part is the sacrifice. You kick it in the direction opposite to the spin, and it falls into the event horizon, disappearing forever. The second part is violently kicked forward by the reaction force, shoots out of the ergosphere, and escapes the black hole's control. the actual energy theft happens right there. Because the spacetime structure of the ergosphere is special, from the perspective of a distant observer's energy bookkeeping, the backward-moving sacrifice can fall into a negative energy state. So when the black hole swallows it, it does not gain energy. It effectively consumes a negative number. The result is straightforward. The black hole loses some of its mass and spin. In other words, we feed the black hole a poison pill that slows its rotation. Meanwhile, the escaping half leaves with more energy than the original object had. Where does the extra energy come from? It is deducted directly from the black hole's spin. After the payload escapes, it can be captured farther away, using ring-shaped collection structures or magnetic coil systems, gradually converting its momentum into electrical energy to power an entire civilization. Put simply, you trade a piece of junk for a massive chunk of usable power. But throwing things in and splitting them is ultimately too crude. For a Kardashev Type 2 civilization, industrialization must upgrade from mechanical to electromagnetic methods. That leads to superradiant scattering. You can think of it as the idea behind a black hole bomb. You surround a rotating black hole with a gigantic spherical mirror shell, then fire electromagnetic waves into the ergosphere. When the waves scatter back out of the twisted spacetime, they become slightly stronger. The key is the mirror. The mirror reflects the amplified wave back in, so it enters again, scatters again, and becomes stronger again. Energy accumulates repeatedly between the black hole and the mirror. Each cycle amplifies it further, eventually rolling into an exponential positive feedback loop. At this point, the engineering challenge boils down to one word: containment. You have effectively built a universe-scale laser. The mirror's shell must have controllable openings and valves, releasing energy rhythmically as manageable beams. Otherwise, the energy density inside the cavity will keep rising. In the end, it will either tear the megastructure apart, or, more extremely, the light will become so dense that it generates its own gravity, and collapses into a new black hole, a Kugelblitz black hole. That means while you are using a black hole to generate power, you are also risking the creation of another black hole. But if you can stabilize it, the payoff is terrifying. On Earth, even the most promising nuclear fusion converts less than 1% of mass into energy. But running the Penrose mechanism on a rapidly spinning black hole can theoretically reach 29%. This is almost the strongest engine physics allows. As long as you keep supplying tradable matter, keeping the negative energy bookkeeping going, or continuously amplifying electromagnetic waves via superradiance inside the cavity, this engine can keep running. So it is not just a massive power station, it is more like a watershed in the history of civilization. Right now, we live in a stellar economy. The sun gives what it gives, and we pick up what we can. At its core, this is passive scavenging. But once you can maintain black hole power, energy scarcity begins to fail as a concept. Planetary engineering, interstellar arcs, megastructures. Many things stop being questions of can we, and become questions of scheduling, allocation, and how to funnel resources into the most critical steps. An even harsher value lies ahead. Not in power, but in longevity. We live in the stellar era. The universe is like a bright summer, full of light and warmth. But summer will end. In the deeper future, star formation will dwindle and eventually drop to zero. Stars will age one by one and go dark. The universe will enter a long, cold winter, leaving only the fading warmth of dead stars. Solar-powered civilizations reaching that stage are effectively facing a blackout. But rotating supermassive black holes are different. They are not fueled by burning matter. They run on gravitational structure and spin. As long as the spin remains, you can keep extracting energy. And that spin is absurdly stable. It can persist for trillions of years. So for black hole farmers, that is not the end, just a change of season. They can use the Penrose process to maintain heated oases during the cosmic freeze, giving civilization a continuous energy source even in the coldest ages. They will gather around the spin of a singularity for warmth, like travelers guarding the last fire in endless darkness. By then, civilizations likely will not live on planets. Planets will become frozen tombs, barely able to sustain liquid water. They will more likely live in safe zones outside the ergosphere, in orbital swarms, in rings of artificial habitats. These habitats will appear to float far from the black hole, but in reality, they are linked by invisible energy channels to the dark engine below. Their identity will fundamentally change. They will no longer be collectors of starlight, but caretakers of spin. They will not be waiting for the sun to shine, but guarding the universe's last stretch of sustainable light. So in this story, black holes are retried and rejudged. They are no longer just devourers, they may be lifeboats. They force us to rethink darkness itself. We always treat the unknown as a monster, but the hints physics gives are more unsettling. Life's final exit may not lie in the light, but in the deepest shadows. We study black holes not only to power machines, but perhaps to keep consciousness alive longer than stars themselves, even long enough to endure the aging of the universe.